Hello YouTube, this is my first video in my module on linear and nonlinear inequalities, and it's kind of a lead into systems of inequalities, but we're going to go ahead and start with just, kind of how you graph inequalities, a little bit of review. So let's go ahead and just take a look at what an inequality is and why we would, and how we would graph them really. So I've got a little example here. We say sketch a solution region. Okay, so we say solution region for this linear inequality, y is greater than or equal to x squared minus 1, okay? You'll notice here I say start by graphing its corresponding equation. The thing is this, when you graph the equation of something, so for example, if we have this equation y equals x squared minus 1, which by the way does have a parent function of y equal x squared, it's just been shifted down 1. We get this graph right here that's a parabola, okay, and so we shift down 1. I notice we have an a value of 1, so we'd say up 1, right 1, and of course we know the general shape of these things, so go up 1, left 1. And just to be a little bit more clear about this, I guess we could put in some more points that I know to be on this graph, but I typically wouldn't. But here's our parabola. When you graph something, of course, when we look at the points on the graph, what we're looking at is a set of solutions to that equation, okay? So if I were to necessarily take one of these points, like this point right here, which is 2, 3, and reinsert it back into the equation, so I'd have this. I'd say y is 3. We get x squared minus 1, where our x value is 2. What I end up with is this statement here, 3 equals 4 minus 1, or 3 equals 3. In other words, we get a true or valid statement. So what you're looking at when you look at the graph of an equation is the set of all things that when you plug it back and make them true, okay? So how does this y is greater than or equal to x squared minus 1 distinguish itself from the equation that we just graphed? The thing is this. The set of solutions is much bigger than what you get here, and I don't want to go into arguments about, well, they both have infinitely many, elements in their sets of solutions, but we say you could think of it as being bigger. And the thing is, there are many more points that are going to satisfy this than would just satisfy just the equation, which is all the points on this right here. So you could think of this graph right here as sort of like a boundary line, okay? So a boundary that separates one side of the solutions of this equation, okay? So we say y greater than or x squared greater than or equal to x squared minus 1. What we're going to do is this. We're going to assume, or not assume, but just I want to understand this. All of the solutions to this inequality, they are going to lie either on kind of like the inside of this parabola here, or they're going to lie on the outside of this parabola here. So when I say that the equation acts as sort of like a boundary, it's kind of what I mean here. All the solutions are really on one side or the other. And so the question is, well, how do you know which side the solutions lie on? And recall this, solutions are just things that when you plug it into the original statement or argument here, it makes them true. So for instance, to graph this, what I would do is, yes, start by graphing the equation, which we've done. But what we'll do is we'll select a point, and we'll call this a test point, okay? So in terms of a test point, we're going to select a point that is either on one side of the boundary or the other side. And I think that a really convenient point to plug in here would be like the point 0, 0. So what we're going to do is we're going to take this point 0, 0, we're going to insert it into the original argument, and what we get in this instance is this y is greater than or equal to x squared minus 1. We're plugging in a 0 here and a 0 here just because it was a convenient point that wasn't on the boundary, okay? So we get this statement here. We say 0 is greater than or equal to 0 minus 1. In other words, 0 is greater than or equal to negative 1. And what I can tell you is this is true. And so since this is true, just like with any graph, you shade in any points that make it true. So hence the boundary line, we put a line on all of those points because they are true makers. What I'll do is I'll put, like maybe a point here because it's true. But the simple fact is this: when you graph inequalities, we said all the solutions lie on one side of the boundary or the other. Well, if 0, 0 satisfies this, then I know that also this point here satisfies it, and this point here satisfies it, and all of these points on the inside here satisfy it. So the brief way to do this is we just shade in the side that contains all of the solutions. So we would say the graph of this linear inequality or nonlinear inequality would be this, and this is the set of all solutions to the original argument. So if we were going to kind of list out the steps that we've taken here in this entire process, number one is this: we sketch the associated equation. So when we say sketch the associated equation, well, when I wanted to sketch y is greater than or equal to x squared minus 1, we sketch y equals x squared minus 1 first to separate the plane into two regions here. So we get this parabola. Step 2 is this: choose a test point. So when we say choose a test point, we're referring to a point Not on the associated equation. So we chose 0, 0 out of convenience. And then step 3 is we are going to test that point. We're going to test the point into the original argument. And then we're going to shade towards the true side. Okay, so shade towards the solution. So I guess we could have said, well, what if this point that we tested 0, 0 would come out to be false? We wouldn't have shaded on the inside of this parabola, we would have shaded on the outside of this parabola. Okay, so what we're looking for is the set of all solutions to this region. Before we wrap this video up, I just want to do a few more examples of linear, specifically linear inequalities, because we spend so much time with systems of inequalities doing linear things. So for example, over here on letter A, we say, well, graph x is greater than -2. And what we're saying is graph all the points that would make this statement true. Okay, well, I want to see them. And so, first we would start with this. We say x is equal to -2. This will serve as, again, like our boundary. So step 1 is graph the associated equation. So when we say x equals -2, what we're talking about is a vertical line here at -2. Okay, so it's kind of a weird thing. But we graph a vertical line here at -2. Now the interesting thing is this, you're going to notice I graphed a solid vertical line. Anybody that has graphed inequalities before will know this. We said x is greater than -2. And so we're going to test a point, and actually if you've already determined this, we're going to shade to the right of this line because that's where all the points that are, all the x values are greater than -2. But the thing is this, we didn't say greater than or equal to -2. And recall that when you shade something or put points on something, it means it makes it true. If we were to say try to plug these back into the original statement, like the point here, like -2, 2. If we were to put -2, 2 into the original statement here, we would get this. We'd say greater than 2, and we put -2. -2 is not greater than 2. So here's what we have to do. We have to acknowledge that when we are graphing inequalities, when you have just a greater than or just a less than and not or equal to, you're going to graph a dotted line. Okay, so when we say this dotted line, that would refer to greater than or less than statements, and we say a solid boundary line is going to refer to anything that is greater than or equal to or less than or equal to. Okay, this is really important. So we're going to go ahead and regraph this. We say x is equal to -2, but you see it's greater than here in this instance, so we are going to graph this dotted or dashed line to the best of my handwriting ability on this bamboo here. And we say, okay, well, then I get this. We do want to label this. So most of the time we'll label this equation. And we say, okay, so now we'll test the point. We said, well, what would be a really convenient point to test that's not on this? In this case, 0, 0 is still an eligible point here. So not that I need to test the point on this, but we'll plug this in for x and in for y in the original statement. And the original statement said this, x is greater than -2. And we are instead putting in a 0 for our x. And we have no y to plug into, so I don't have to worry about plugging that in. And I get this statement. I say 0 is greater than -2, which is indeed true. So what this means is I am going to shade that point, but I'm also going to shade all points to the right of this. So we can actually shade the entire half plane. What I would actually give people the suggestion of doing, since you're going to be doing systems here eventually, is just shade this way by drawing an arrow to the right, because we're eventually going to have lots of inequalities overlapping, and it's good to look for the confluence or where all the arrows come together. Okay, so really quickly we'll finish up these next two. We say y is less than or equal to -3, so we're going to graph y equals 3 first, and it would be a solid line because it's less than or equal to. So here is our boundary line here, and it is solid. We're going to go ahead and label this. We say y equals 3. When you label the boundary, we always use an equal sign, not the less than or greater than stuff, because that doesn't refer to the line itself. Only the equation refers to the line. And we say, okay, so which way should I shade? Maybe I'll test 0, 0. 0, 0 is not on my line. We'll plug in a 0 for my y here, so we get this. We say less than or equal to 3. Plug in 0, and I get another true statement. So if this point's true, all of the points below this boundary line must be true, so we'll shade down. So we say all of the solutions lie in this region of the half plane region here. And then last but not least, we see something that is not just a y equals or an x equals kind of situation, but x minus y less than or equal to 2. I will say this really quickly. A lot of people, when they see this and they say, well, I want to graph it, Okay, they would subtract x from both sides, and you get this statement here. You get 2 minus x, and they put it in slope-intercept form, and they divide everything by a -1, and they make this mistake. They say, well, -2 plus x, and the thing here is this: when you divide or multiply an inequality by a negative, you have to switch this inequality sign. So, for instance, I could put this in slope-intercept form, but I am responsible for changing this. It would be -2 plus x. And so I could say, well, this has a y-intercept of -2, and a slope of 1 here. So I go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, and it'd keep doing this indefinitely. My suggestion is going to be this instead. Whenever you have something not in standard or slope-intercept form, but in standard form, what we'll do is this. We'll find its intercepts. And of course, the way you find an intercept is this. If you find an x-intercept, you plug in 0 for y. When you find a y-intercept, you plug in 0 for x. So for instance, if I were to plug in a 0 for y and say, where does this hit my x-axis? If I put in a 0 right here for my y, you notice I get this. I get x minus 0 equals 2 if we're doing the equation. So I get x equals 2. And of course, I'd go draw a dot at x equals 2 on my x-axis, say it hits my x-axis at 2. And likewise with my y here, we'd say, okay, well, if I plug in a 0 for x, I would get 0 minus y equals 2, so y equals -2, and I draw a dot on -2 on my y-axis. So finding intercepts is actually, in standard form, a lot of the time more convenient. But now that I've got my intercepts, I say, well, solid or dotted line. In this instance, we're going to have a dashed dotted line, and the reason being is because this is just a less than equation. We're going to label this, so we say x minus y equals 2 when we're labeling just the boundary here. And now we need to test the point. And of course, 0, 0 being not on the boundary equation, we could test 0, 0 and see, is it true when I plug it in or not? So I get, in the original statement here, I get this, x minus y less than 2. So I get 0 minus 0 is less than 2, or 0 is less than 2. And since this is true, I would put a dot on 0, 0. But also, since I would put a dot on 0, 0, I would put a dot on anything. I would shade anything that happens to lie on this side of my equation. So we would shade this entire half plane here. So that's how you would graph inequalities in general.